Okay, so in the last section, we had a very lengthy discussion about tests about general tests of significance. In this section, we are going to specifically talk about tests about a population proportion. And hopefully some of this is a review of what you've seen in the past. So we're just taking what we have learned in the last couple of units and sort of piecing it all together and see how statisticians actually do tests about a population proportion. All right, so in this section, once again, we're going to be back to that stating and checking your 10% condition, large counts condition, and basically taking a look at our assumptions and conditions to make sure our data in our population is approximately normally distributed. We're going to learn how to actually perform a test about a population proportion. So just two little things. All right, so let's go back to our basketball player. Remember he thought he was pretty awesome and that he claimed that he got his free throws 80% of the time, but we did a simple random sample. He only made 32 out of the 50. And so his sample of proportion made shots was 0.64. And we said, whoa, that was actually much lower than what he claimed. Are you really as good as what you say you are? So our question is we said, hey, he's actually not as good as he says he is, because if he was as good as he said he is, the probability of getting this statistic was pretty low. So we're going to actually go through and show how we can statistically prove whether or not we have evidence against his claim. All right, so before we do a significance test, we're going to go back to what we talked about. We have a claim that we are testing against, all right? Are we providing convincing? And remember, we're doing evidence. We're never proving whether the null alternative is correct. We just have evidence for or against the null. So the test that we're looking at is we're assuming that the null, hey, he does make 80%. Yeah, he's pretty good. But we're like, wait a second, we actually don't think you make 80%. So we're testing the proportion of your free throw shots is actually less than 80. And notice how P is defined. It's the true proportion of free throws the shooter makes in the long run. So what exactly are the steps for performing a significance test to see whether or not he actually does make less than 80% of his shots? Okay, so this is just the general steps for your test of significance. This is what you're going to see every single time you do one, whether it's this, means, we'll get into chi-square tests and other stuff. All right, step number one is you're identifying the parameter and stating the name of the test you'll be using. So one sample z-test for proportions, we'll go over what all that means. You're going to write the assumptions and conditions. So it's the same thing you did for confidence intervals. The assumptions and conditions are making sure we have a simple random sample that allows us to provide inferences to the larger population, has to be approximately normal, and we need to prove that it's independent so that we can use that standard deviation. We're going to state the null and alternative hypothesis. So what exactly are we testing? Make sure you define what P or mu is. We're going to find the critical values. So what are your critical values? Your critical values are your z-scores in this case that we are going to sort of, the critical values are on your curve that you're rejecting or failing to reject the null. So sort of like in confidence intervals, we're rejecting, or sorry, in the last section we had that line the alpha line that we were rejecting or failing to reject the null. We're going to find the z-score that goes with that area that defines the difference between rejecting and failing to reject the null. You're going to draw a normal curve, label the critical values on the curve, and the critical values come from your alpha value. And we'll go over how to do that. We'll find the test statistic, so that is basically your z-score, how far away your statistic is from the population mean or proportion, what we think it is, and the p-value, and that's the probability that your specific statistic is going to occur. And then we're going to make a conclusion to reject or fail to reject the null based on the alpha value that we've chosen. Finally, we're going to write a non-mathematical conclusion that includes the interpretation of the p-value, and I'll go over what that is. We kind of looked at that in the last section, and this is where you're going to use the template for the conclusion for your TOS. So TOS just stands for test of significance. All right, make sure if it's easier for you to print that out from Blackboard, have it in front of you as you're doing it, and then hopefully you once you do it a bunch of times, you will say, hey, this is actually pretty easy. Okay, so in this section, you're going to have two names of tests. The first one is going to be a one sample z-test for proportions, and the other one is a one sample z confidence interval for proportions. So you already know how to do a one sample z confidence interval for proportions. You know how to create and construct a confidence interval. In this section, we'll actually be showing you how to use a confidence interval to test a claim, which is different. Now, where the names come from, one sample, because we're actually given only one sample that we're testing. It's a z-score because we're using the standard normal curve with z calculations. For proportions, because we're actually looking at proportions. All right, so how do we carry out a significance test? So what are the three conditions for conducting a test of significance for the population proportion? How are these different than constructing a confidence interval for a population proportion? Now, just remember, these are the same things that we talked about in a confidence interval section. One, we have to have a simple random sample. Why? Because if we don't have a simple random sample, I can't take the results that I have and use it for inference for a larger population. They're sort of stuck in the sample that I have. Two, you need to have independence. So that's when you're sampling without replacement, the population has to be 10 times the sample size because we have that square root of n in the denominator to show that each of those values are independent of each other. And since this is specific, this is the hardest part here because this is the one that changes between means and proportions, is the large counts condition. Both NP and n times 1 minus p have to be at least 10. So remember that's that balancing point that makes your curve approximately normal. So since we're using z-scores, we have to have a normal curve. Now notice here, this is using the population proportion, not the sample proportion, because the large counts condition is about the population, not that specific sample. So when you check the normal condition, you want to use the population proportion, not the sample proportion. Okay, why is that? We're assuming that the null is true, so we're using the population proportion instead of p hat. This is different from confidence intervals because with the confidence interval, we didn't have p. We didn't have anything that we were testing against, so we used the sample in order to check the large counts condition. All right, so when the conditions are met, we have a simple random sample, independence, and the normal condition. Remember that the sampling distribution of p hat is approximately normal. Our mean of our sampling distribution is the same as the population proportion, and the standard deviation of the sampling distribution of p hat, notice how you have those p hats there, is p, your population proportion or your null, times 1 minus p divided by n. So the z statistic, in this case we're talking about z statistic, it's going to have a normal distribution with this mean and this standard deviation. The p-values is the probability using your z-statistic that z-statistic could occur, that value, that extreme or more extreme, that p-value is just a probability that comes from the normal distribution. Now, what's the critical value? The critical value just comes from the alpha value. It's the same as finding the critical value for the confidence interval. The critical value is going to depend on if the test is one-sided or two-sided. It will be positive if the test is greater than 0, if we're checking to see, or not greater than 0, if we're checking to see if our alternative is greater than the population, and negative if we're checking to see if the test is less than the population. So this PO, that's basically like your null. Okay, that's actually, it would always have a value in there. So what this is saying here is if we're checking to see if we think that the null is too low and we think it should be higher, all right, right here you always use the top end of the curve. Here's your z-score right here. All right, let's just say that this is alpha is 5% and this would be 95%. You're going to find the corresponding z-curve that sort of separates the fail to reject and the reject the null region. So same thing down here, p is less than what we think the null should be, so that means you're on the left-hand side of the curve. If it's not equal to, then we're not sure whether our alternative is greater than or less than, so we take into consideration both areas on the curve. Okay, all right, so this critical z-score is 1.65. That should actually have a percentage. That's when alpha is 0.05. So right here we have, you would take the inverse norm of 0.95, that's the area to the left, and then the area to the right is 5%. Okay, so there's your rejection region for that one, and here's where we're failing to reject it. Same thing, z is negative 1.65. Why is it? Because it's to the left of what the null is. Okay, the alpha is 0.05. To get that alpha value, we just do inverse norm of 0.05 because this z-score right here, it's separating what we're rejecting and failing to reject. So what is the area under the curve? That's 5%. So we're going to do inverse norm of 0.05. And then for the last one, we have two rejection regions. And so we have actually two z-scores, negative 1.96 and positive 1.96. Because if our alpha is 0.05%, what that means is I'm rejecting it 2.5% of the time up here and 2.5% of the time down here. So when I do my inverse norm to get this z-score between the fail to reject and reject, I have to do inverse norm of 0.975 because I have 95% of the 95% of the curve in here plus the 2.5% in this rejection region. You could also do inverse norm of 0.025, okay, because I have 2.5% in this region. All right, so what does a significance test do? A significance test uses sample data to measure the strength of the evidence against the null. So just remember, the further that your sample is from the null, then that is going to be more evidence that the null is actually false. So what does it do? The test compares a statistic calculated from the sample data with the value of the parameter stated by the null. So all this is saying is it takes the statistic, our sample that we have, and compares it. How far away is it actually from what the null value is? Values of the statistic that are far from the null, they give lots of evidence against the null and in favor of the alternative. So what is a test statistic? So since we're talking about test statistics and how far away they are from the null, think about that. That's basically like your z-score. It's the same thing as your z-score. You're taking your statistic, you're seeing how far away it is from the parameter or from the null that we've stated, and then we're going to divide it by the standard deviation of the statistic, which is literally the exact same thing as a z-score. Okay, so what is a test statistic? What does it measure? Is it a formula on the formula sheet? Absolutely, it's on the formula sheet because all z-scores are on the formula sheet. The test statistic is just the z-score for the sampling distribution. So the test statistic for proportions is p hat, your sample, how far away it is from the null, and divided by the standard deviation. Now, here's the tricky part here. Notice that since we are using a z-score curve, we have to use the population proportion. All right, we're using what the null is because we're using a z-score curve, and that's based on this. So no matter what statistic that I get, this down here is going to be, the standard deviation is going to be the same every single solitary time, which is different with t-scores, because with t-scores, we use the sample standard deviation because we didn't have the population. But in this case, we have the null. We're assuming the null is the same as the population, so you're going to use the population in the standard deviation, not the sample. Okay, basically it measures how far away from the parameter or null is that a sample is. The general formula is on the formula sheet. You just have to put the two together. So this is on the formula sheet. The z-score formula from the previous page is on the formula sheet. You just have to know, hey, here's my two pieces, smash them together. Okay, so here's what's on your formula sheet. Boom. Here's what we know this is. Boom. Okay, so what is the p-value? So to test the hypothesis that the null is equal to some specific value, you find the p-value by calculating the probability of getting a z-statistic this large or larger in the direction specified by the alternative. So what does that mean? So if I'm testing the probability that I think it's actually greater than the null, then when I find my z-score and see how far away it is from the null, I'm going to test the probability that I get that z-score or larger than that z-score that I got. So what's the probability that I got that value that far away from the mean or another value further than that from the mean in the direction, the positive direction? So down here, if I'm testing and I say, hey, I think it's actually less than, all right, what I'm going to do is I'm going to take the z-score and I'm going to see if it's less than the test statistic. So I'm going to do the probability that z is less than, because my z-score is most likely going to be smaller than what the null is. So how far away that z-score is from the null, is it going to be that value? What's the probability of getting that value or less? That's going to be your probability. And then if it's not equal to, you actually just find both of them and add them together. So what's the probability that I get a z-score above the null, that extreme or more extreme? What's the probability that I get one below the z-score, that value or less than that? And since because it's symmetric, you can just add the two together, they'll be exactly the same. All right, so what happens when the data doesn't support the null? If the data does not support the alternative, then we're failing to reject the null. We don't have enough convincing evidence that the null is false. Most likely the result that you got was due to random chance and isn't statistically significant. So it's just one of those things that happen. You got this, it was due to random chance, it was one of the possibilities that could actually be true. And this most likely means you didn't even need to carry out the test. So we're always checking to see whether the data gives evidence against the null in the direction of the alternative before you do the calculations. Remember, you fail to reject the null, you never accept it.